There is a number in the back of almost every astronomy book that should not be able to sit where it does. The universe is 13.8 billion years old. The furthest thing we can see is 46.5 billion light years away. Light has had 13.8 billion years to travel, so the edge ought to be 13.8 billion light years out, not 3.5 times further. That gap is not a misprint, and no better telescope will ever close it. Folded inside it is the reason that 95% of the galaxies above you tonight are already permanently out of reach. Not out of reach of our rockets, out of reach of light itself, emitted this evening, given all of eternity to arrive. By the end of tonight, you will know exactly what it takes to reach the edge of the universe, and why we will never make it. And the strangest part is that it gets no easier if you make the ship infinitely fast. Get comfortable. If you enjoy having your sense of scale quietly dismantled, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the word edge will not mean what it did this morning. Now let's slowly settle in. There are two numbers that appear together in almost every reference work on cosmology, and almost nobody stops long enough to notice that they should not be able to sit next to each other on the same page. The first number is the age of the universe, 13.787 billion years, give or take about 20 million. That figure comes from the Planck spacecraft's final analysis of the cosmic microwave background, and it is one of the best measured quantities in all of science. It is not a guess or a rounded estimate. It is a number with error bars so tight that the uncertainty is smaller than the time between the extinction of the dinosaurs and the invention of writing, expressed as a fraction of the whole. The second number is the size of the observable universe. The distance from here to the furthest thing we can see is 46.5 billion light years. The full diameter, edge to edge through us, is about 93 billion light years. Now hold those two numbers together for a moment and let the arithmetic do what arithmetic does. A light year is the distance light travels in 1 year. That is the definition, and it is the whole definition. Nothing carrying information travels faster than light. The universe has existed for 13.8 billion years. Therefore, the furthest thing whose light could possibly have reached us should be sitting 13.8 billion light years away, not 46, 13.8. That is what the arithmetic says, and the arithmetic is not being subtle about it. The observable universe is more than 3 times larger than it has any business being. When most people encounter this for the first time, the reflex is to assume a mistake somewhere. Maybe the age is wrong. Maybe the distance is measured in some technical way that does not mean what it sounds like. Maybe there is a factor of 3 hiding in a definition somewhere, and the whole thing dissolves once you read the footnote. That reflex is reasonable, and it is also wrong. There is no typo. There is no hidden convention. Both numbers mean exactly what they appear to mean. Both are correct to within a few percent, and the gap between them is not a measurement problem that better instruments will close. The gap is the most important physical fact about the shape of the universe. Everything else in this video comes out of it, and tucked inside that gap is the question this video is actually about. Because if there is an edge out there, if there is a furthest place 46.5 billion light years away, a boundary to what exists as far as we can tell, then the obvious question is the one a child asks and an adult stops asking. What would it actually take to get there? Not in the vague way people mean when they say space is big. Specifically, what ship, what fuel, what speed, what number of years? What is the actual bill? By the end of tonight you will have that answer, and it is not the answer anyone expects. It is not that the edge is too far away. It is not that we lack the technology, or the energy, or the patience. Those are all true, and all 3 of them turn out to be the least interesting reasons. The real answer sits underneath all of them, and it is stranger than any of them, and the peculiar thing about it is that it does not get any easier if you make the ship faster. It does not get easier if you make the ship infinitely fast. That is the part that takes some getting to, so we're going to get to it slowly. Let us start by being precise about where that number comes from, because it is not a vague estimate. The figure of 46.5 billion light years traces most directly to a paper published in 2005 by a group at Princeton, including the astrophysicist Richard Gott, titled simply A Map of the Universe. They set out to draw the whole thing on a single page, an honest map with everything on it, from the Earth's orbit out to the last surface anything is visible on. And to do that, they had to be careful about what distance meant at every scale. The number that came out the far end of that care was 14.26 gigaparsecs, which converts to 46.5 billion light-years. It has been refined slightly since. It has not been overturned. It is worth pausing on what that sphere contains, because the number is doing a lot of quiet work. The most widely quoted estimate is 2 trillion galaxies, a figure that came out of a 2016 analysis that took the galaxies we can count and extrapolated downward to the ones too faint to see. That number has been challenged. A later measurement, using the camera aboard the New Horizons spacecraft, from a position far out beyond the dust of the inner solar system where the sky is genuinely dark, put the total closer to a few hundred billion. The two answers differ by a factor of 10, and the disagreement is not resolved. So when you hear anyone say what fraction of the universe we could reach, hold that factor of 10 in the back of your mind. We are working in orders of magnitude here, not decimal places, and the argument survives that comfortably. And it helps to understand what the outermost surface on that map actually is. It is not a wall. It is the cosmic microwave background, the moment, 380,000 years after the beginning, when the universe cooled enough to stop being an opaque fog of charged particles and became transparent. Before that instant, light could not travel freely. It scattered off free electrons the way headlights scatter in thick cloud. After that instant, light could cross the universe unimpeded, and the first light released in that transition is still arriving here tonight, from every direction, at a temperature of 2.725 degrees above absolute zero. That surface sits at 45.5 billion light-years, just inside the outer boundary. It is the furthest thing we can see, and we can see it in every direction at once, and it is not an edge. It is a fog bank. There is more universe behind it. We simply cannot look through it with light. That distinction is going to matter enormously later, so it is worth planting now. The outermost thing in our sky is not the last thing that exists. It is the last thing that has finished being visible. Now back to the arithmetic problem, because we have not solved it yet. We have only made it more specific. Light has been travelling for 13.8 billion years. The furthest thing we can see is 46.5 billion light-years away. Somewhere between those two statements something has to give. And here is what has to give. It is not the speed of light. It is not the age. It is your assumption, my assumption, everybody's assumption, that the distance between two things is a fixed quantity that only changes if one of them moves. That assumption is so deep that it barely feels like an assumption. It feels like what distance means. If a car is 100 meters away and neither of us moves, it stays 100 meters away. If it is still 100 meters away an hour later, nothing has happened. Distance, in ordinary life, is inert. It sits there. It has to be acted upon by motion to change. That is true for cars. It is true for continents. It is true for planets, and for stars, and for the distance from here to the far side of our galaxy. It holds up beautifully at every scale you will ever personally encounter, and at quite a few you will not, and it stops being true somewhere out past the edge of the local group of galaxies, which is where this whole story properly begins. Because the space between distant galaxies is not inert. It is not a gap that sits there waiting. It is growing, not because the galaxies are flying apart through space like debris from an explosion, which is the picture almost everyone carries and which is wrong in an important way, but because the space itself, the distance itself, the thing that the measurement is a measurement of, is getting larger. Everywhere. All the time, including right now in the gap between here and everything. That is the resolution to the arithmetic. A photon that has been travelling for 13.5 billion years has covered 13.5 billion light-years of ground. But the ground moved underneath it while it travelled. The gap it was crossing kept opening. It arrived, eventually, and by the time it arrived, the place it left was no longer 13.5 billion light-years away. It was 34 billion light-years away, and still going. The distance to the edge of the observable universe is not a distance light has travelled. It is a distance that has grown, which sounds, on first hearing, like a technicality, a bookkeeping adjustment, a footnote for cosmologists. It is not. It is the reason that most of the universe you can see tonight has already been placed permanently out of reach, not out of reach of our rockets, out of reach of light itself, emitted this evening, given all of eternity to arrive. It is the reason that a working faster-than-light drive would not help, and it is the reason that the phrase "the edge of the universe" describes something that is not, in any sense that would let you travel to it, a place. But before any of that can make sense, we need to look properly at the thing that is doing all the work here. We need to look at what it actually means for space to stretch, and at what that stretching does to a beam of light that has been caught in it for 13.5 billion years. The picture almost everyone carries of the expanding universe is an explosion. Something detonated a long time ago at a particular spot, and all the galaxies are the shrapnel, flying outward through space, getting further apart because they are moving apart, the way debris from a firework gets further apart. That picture is wrong, and it is worth taking a minute to dismantle it properly, because almost every confusion about the edge of the universe comes from keeping it. The galaxies are not, for the most part, moving, not in the sense that matters here. Every galaxy has some local motion, a few hundred kilometers per second of drift relative to its neighbors, the way a leaf on a river has its own small motion relative to the water. But that local drift is trivial compared to what is actually separating them. What is separating them is that the distance between them is increasing on its own, with no motion involved at all. The standard image people reach for is raisins in a rising loaf of bread. As the dough expands, every raisin gets further from every other raisin. No raisin is moving through the dough. No raisin is at the center. And here is the part of the analogy that actually earns its keep. From the point of view of any given raisin, all the other raisins appear to be moving away, and the ones furthest away appear to be moving away fastest, because there is more dough between you and them, and all of it is expanding at once. That last detail is precisely what Edwin Hubble measured in 1929, and it is why the relationship carries his name. The velocity at which a galaxy recedes from us is proportional to how far away it is. Twice as far, twice the recession. 10 times as far, 10 times the recession. The constant of proportionality is called the Hubble constant, and the best current value sits somewhere between 67 and 73 kilometers per second for every megaparsec of distance, which is to say, for every 3.25 million light-years you go out, the recession speed increases by about 70 kilometers per second. The fact that there are two competing values there, and that they disagree by more than their error bars allow, is one of the great open problems in physics at the moment. We're going to leave it alone tonight. It shifts every number in this video by a few percent and changes none of the conclusions, which is why every figure you hear from here on is given to 2 significant digits and no more. But the raisin loaf has a flaw, and it is the flaw that matters most. A loaf of bread has a crust. It has an outside. It sits in an oven, which sits in a kitchen. There is somewhere for it to expand into. The universe has none of that. There is no outside for it to expand into, no surrounding space it is pushing against, no edge to the dough. The expansion is not the loaf getting bigger within a larger kitchen. It is the recipe for distance itself changing over time. If you could freeze the universe and lay a ruler between 2 distant galaxies, and then wait 1 billion years and lay the same ruler down again, you would need more rulers. Not because anything moved, because there is more distance there than there used to be. And this is where light gets caught in it. A photon travelling between 2 galaxies is moving through space at exactly the speed of light, as measured by anyone standing anywhere along its route. That never changes. What changes is the space it is moving through, which keeps stretching underneath it. And because a photon is a wave, and because a wave has a wavelength, a physical length, a distance from crest to crest, when the space carrying that wave stretches, the wave stretches with it. The light gets longer, it gets redder, and it keeps getting redder for as long as it is in flight. This is redshift, and it is the single most useful measurement in cosmology, because the amount of stretching tells you exactly how much the universe has expanded since that light was emitted. A galaxy at what astronomers call redshift 1 emitted light that has since doubled in wavelength, which means the universe has doubled in size since it left. Redshift 2 means the universe has tripled. The relationship is that simple. The universe was smaller than it is now by a factor of 1 plus the redshift. Which brings us to the current record holder, and to the numbers that make this concrete. The most distant galaxy anyone has ever confirmed is catalogued as MOM-Z14. It sits at a redshift of 14.44. Its light was emitted about 280 million years after the beginning, which on the scale of the universe's life is roughly 2% of the way in. If you compressed the whole history of the universe into a single year, That light left in the first week of January. It is worth noticing how recently that record was set and how quickly it keeps changing hands. For most of the last decade, the benchmark was a galaxy called GNZ 11 at redshift 10.6, found with Hubble and confirmed spectroscopically only after Webb came online. Then in 2024 came a galaxy from the Webb Deep Survey at redshift 14.32, seen about 290 million years after the beginning and unexpectedly bright and large for its age, something like 1,600 light-years across, which nothing that young was supposed to be. Then MOMZ14 took the title. The teams publishing these results have stopped hedging about what comes next. The papers now say plainly that redshifts approaching the era of the very first stars no longer look far away. The frontier of what we can see is being pushed outward every single year. Hold on to that, because in about 40 minutes we are going to look at a second frontier that is moving in exactly the opposite direction. A redshift of 14.44 means the universe has expanded by a factor of 15.44 since that light departed. The wavelength of every photon in that beam has been stretched 15-fold. Light that left as ultraviolet, hot, young, energetic starlight, the kind of light a brand new galaxy full of enormous short-lived stars pours out, arrived here as infrared. It arrived as heat, and that, incidentally, is the entire reason the James Webb Space Telescope is an infrared instrument sitting 1.5 million kilometers from Earth, being kept at 40 degrees above absolute zero. The early universe does not emit infrared. It emits ultraviolet. The expansion of space does the translation, and it does it so thoroughly that a telescope built to see visible light is simply blind to the first billion years. Hubble could not see these galaxies. It was not a question of aperture. It was looking in the wrong part of the spectrum because the universe had moved the picture. Let me put you inside that. You're a single photon, leaving a young galaxy about 280 million years after the beginning of everything. The universe around you is 15 times smaller than the one you will arrive in, and correspondingly denser and hotter and more crowded. Galaxies are close together. The sky, if anything were there to look at it, would be crammed. You leave as ultraviolet, short, tight, high energy, the wavelength of the light that burns skin. You travel. There is nothing to travel through, really. Space out here is emptier than any vacuum ever produced on Earth, and you cross it without touching anything at all. And as you go, you get longer, not suddenly, continuously, imperceptibly, over billions of years, every crest of you drifting further from the crest behind it as the space between them widens. Ultraviolet becomes violet. Violet drains through blue and green and yellow toward red. Red slides out of visibility altogether and becomes warmth, and then something even cooler than warmth. Around you, entire generations of stars ignite and burn out. The first galaxies collide and merge and become the ones we would recognize. 9 billion years into your flight, in a spiral arm of a galaxy that did not exist when you left, a star forms with a disk of debris around it, and in that debris a planet cools and grows an ocean. You're still traveling. You have been traveling for 13.5 billion years when you finally strike a mirror in orbit around that star system, gold-coated, folded and unfolded like origami, and you register as a single faint infrared detection, and the place you left is now 34 billion light-years away. That last number deserves to be said again, because it is where all of this has been heading. That photon travelled for 13.5 billion years. The galaxy that emitted it is not 13.5 billion light-years away. It is 34 billion light-years away, and the gap is still growing. The same stretching, incidentally, is what cooled the cosmic microwave background. That light was released when the universe was about 3,000 degrees, the temperature of a dim orange star, glowing everywhere at once, so that the entire sky in every direction was the colour of a candle flame. It has been stretched by a factor of about 1100 since. It arrives at 2.725 degrees above absolute zero, which is why the sky is dark and cold instead of orange and blinding. The universe did not stop glowing. It just got redder than our eyes can follow, and there is a check on all of this that is worth knowing about, because it is the thing that separates this story from a story. If the redshift were caused by light simply getting tired over long distances, which is an idea people have proposed more than once, then distant objects would look red but would otherwise behave normally. They do not. A supernova at redshift 1 takes twice as long to brighten and fade as an identical supernova nearby. Its entire light curve is stretched in time by exactly the same factor as its wavelength. The universe is not just stretching the light, it is stretching the events. So the arithmetic works, the gap is explained. Light travelled for 13.5 billion years, and the ground kept opening, and that is why the edge sits at 46.5 billion light-years instead of 13.8. Except that explanation opens a door onto something considerably stranger. Because if the space between us and a distant galaxy is growing, and if it grows faster the more of it there is, then somewhere out there is a distance at which the gap is opening faster than light can close it. There is. It is closer than you would think, and we can see straight past it. If the recession speed of a galaxy is proportional to its distance, then the arithmetic runs somewhere uncomfortable very quickly. Take the Hubble constant, 70 kilometers per second per megaparsec roughly. Go out 1 megaparsec and the recession is 70 kilometers per second. Go out 100 megaparsecs and it is 7,000. Go out 1,000 and it is 70,000 kilometers per second, which is already a fifth of the speed of light. Keep going. There is nothing in the relationship that stops. The distance at which the recession speed equals the speed of light has a name. It is called the Hubble radius, or the Hubble sphere, and it sits at about 14.4 billion light-years. That is not a coincidence of numbers, incidentally. It is the speed of a light divided by the Hubble constant, and it happens to come out close to the age of the universe expressed in light-years, which is one of the reasons the two get confused so often. Beyond 14.4 billion light-years, galaxies are receding from us faster than light. Not approaching that speed, not near it, past it. Every galaxy in the sky with a redshift above about 1.5 is currently moving away from us faster than a photon can travel, and in any deep survey image, any of the famous long exposure fields where a patch of empty sky turns out to contain 10,000 galaxies, the overwhelming majority of what you're looking at is in that category. Take the record holder from the last part. MOM Z14 sits at about 34 billion light-years. Multiply that by the Hubble constant, and you get a recession speed of roughly 700,000 kilometers per second. That is about 2 1/3 times the speed of light. It is receding from us, right now, at over twice light speed, and we have its spectrum. Now, the reasonable objection at this point is the one everybody has, and it is a good objection, and it deserves a real answer rather than a hand wave. Nothing can travel faster than light. That is not a rule of thumb or an engineering limit. It is the central structural fact of special relativity. It has been tested to absurd precision for over a century, and every particle accelerator on Earth confirms it every single day. Push a proton harder and harder, and it does not exceed light speed. It just gets heavier and heavier in a way that makes the remaining gap cost more and more energy, without limit. The speed of light is not a speed limit in the sense of a law, with a penalty. It is the shape of the road. So how can a galaxy be receding at 2.3 times that? The answer is that it is not moving. Special relativity forbids anything from moving through space faster than light relative to a local observer. Every word in that sentence is doing work. Through space, relative to a local observer. Both of those qualifications are essential, and both of them are routinely dropped in popular retellings, which is why the confusion is so widespread. A distant galaxy is not moving through space. It is, to a very good approximation, sitting perfectly still in its own patch of the universe, exactly as we are sitting perfectly still in ours. If an astronomer in that galaxy fires a laser, they measure it leaving at 299,792.458 kilometers per second, the same as we would. Nothing local is out of order. Nothing has been accelerated. No energy has been spent. There is no frame anywhere in the universe in which that galaxy is moving superluminally, because in every frame you can construct it is not moving at all. What is increasing is the amount of space between us, and there is no rule anywhere in physics that limits how fast space can grow. That is the whole answer. It is not a loophole or a technicality, or a case of physicists redefining a word to avoid an embarrassment. It is a genuine and important distinction between two things that ordinary language treats as identical: motion and separation. On Earth, the only way for separation to increase is motion, so we use the words interchangeably and never suffer for it. Out here they come apart, and the rule that governs one of them says nothing at all about the other. And once you accept that, something even stranger follows, which is that we can see these galaxies at all. Think about what has to happen for that light to reach us. A photon leaves a galaxy whose recession from us exceeds the speed of light. It heads straight toward us at light speed. But the space it is crossing is being carried away from us faster than that. So for a while, and it can be a very long while, the photon's actual distance from us increases. It is aimed directly at us, travelling at the fastest speed anything can travel, and it is getting further away. It is a swimmer in a river running faster than they can swim. Head down, perfect form, pointed straight at the bank and going backwards. What saves it is that the river slows, or more precisely, the Hubble sphere grows. As the universe ages, the expansion rate per unit distance falls, and the radius at which recession equals light speed moves outward. If the photon can hold on long enough, that boundary sweeps past it from behind, and from that moment onward it is inside the sphere, and it starts making real progress toward us. Every photon we have ever detected from a galaxy above redshift 1.5 did exactly this. It went backwards first. It lost ground for hundreds of millions of years, sometimes billions, before the geometry turned in its favour. The deep field images that hang in every planetarium foyer are made of light that spent the first stretch of its life falling behind. And the light is still arriving. That is the reassuring part of this, and it is worth sitting with, because we are going to come back to that exact sentence later, and it will not be reassuring at all. Right now, tonight, photons are still landing on telescope mirrors from galaxies that have been receding faster than light for the entire history of the Earth. The connection is unbroken. The correspondence is ongoing. Nothing has been lost yet. That is genuinely the good news, and it is why the sky looks so full. But notice what the mechanism actually depends on. It depends on the Hubble sphere growing outward fast enough to sweep past the photon before the photon gives up. It depends on the expansion rate falling over time, and that assumption was perfectly safe for most of the 20th century, because everyone assumed the expansion was slowing down. Gravity pulls. The universe is full of matter. Matter attracts other matter. Whatever set the expansion going at the beginning, gravity has been working against it ever since. And the only real question, the question that most of observational cosmology was organized around for decades, was whether there was enough matter to eventually stop the expansion and pull everything back, or whether it would coast outward forever, slowing but never quite halting. Nobody was asking whether it might be speeding up, because there was no reason on Earth or off it to think that it could be. In 1998, two competing teams measuring the brightness of distant exploding stars found that it is. The method they used is worth understanding, because the whole modern picture rests on it. A particular kind of stellar explosion, a white dwarf that has pulled enough material off a companion star to tip past a critical mass and detonate, always goes off in roughly the same way, and therefore always reaches roughly the same peak brightness. Astronomers call these standard candles. Measure how bright one looks, compare it to how bright you know it should be, and the difference gives you the distance. It is the same logic as judging how far away a streetlight is when you already know the wattage of the bulb. The two teams, one working out of Berkeley, one an international collaboration led from Australia and the United States, were using those explosions to measure how much the expansion had slowed. They both expected the distant supernovae to look slightly brighter than a coasting universe would predict, because in a decelerating universe, the light would have had less distance to cover. Instead, the distant supernovae looked fainter. Consistently in both datasets, independently collected. Fainter meant further. Further meant the expansion had been slower in the past than it is now. Something is pushing the universe apart, and it has been getting the upper hand for about the last 5 billion years. We call it dark energy, which is a name and not an explanation. It accounts for roughly 69% of the total energy content of the universe, against about 31% for all the matter, dark and ordinary combined. Everything you have ever seen or touched or measured directly makes up something under 5% of what is out there. That result took the Nobel Prize in 2011, and both teams spent months before publication trying to find the error because the finding was so unwelcome. It has held up under every subsequent test, and it changes everything in this story, because an accelerating expansion does not just make the universe bigger. It draws a second boundary in the sky, one that nobody was expecting, one that is much closer than the edge, and one that we are already on the wrong side of. Before we can look at it properly, though, we have to deal with the word we have been using loosely this whole time. We have to be honest about what the edge of the universe actually is, because it is not what almost anyone pictures, and the moment you see clearly what it is, the question of how to travel there starts to fall apart in your hands. We have been saying, The edge of the observable universe for 3 parts now as though it were a location. It is time to stop because it is not one, and everything about the question in the title depends on understanding why. Start with something you already know, but may never have taken seriously. Every telescope is a clock. Light takes time to arrive. When you look at the moon, you're seeing it as it was 1¼ seconds ago. When you look at the sun, you're seeing it as it was 8 minutes and 19 seconds ago. If it stopped existing right now, you would have 8 minutes of ordinary afternoon before you found out. The nearest star system is 4¼ years back. The centre of our own galaxy is about 27,000 years back. The light leaving it tonight will not arrive here until long after every language currently spoken has been forgotten. There is no way around this and no exception to it. You cannot see anything as it is. You can only see things as they were, and the further away they are, the further back you are looking. Distance and time are not 2 separate measurements out here. They are one measurement, read off 2 different dials. Now apply that consistently and follow it all the way out. Look 1 billion light years away and you are looking 1 billion years into the past. Look 10 billion light years away and you are looking 10 billion years into the past. Keep going, and eventually you reach a point where you are looking back as far as there is anything to look back at, where the look-back time equals the entire age of the universe, and there is simply no earlier. That is the edge. It is not a wall, it is not a shell or a surface or a boundary of any physical kind. It is the point at which you run out of past. The reason you cannot see anything beyond it is not that something is in the way. It is that light from further out has not finished arriving. It has been travelling for 13.8 billion years, and it is not here yet. The edge of the observable universe is not a place. It is an age wearing the costume of a distance, and once you say it in those terms, several things fall out immediately, each one stranger than the last. The first is that the edge is centred on you. Because the horizon is defined by light arriving at a particular point, every point gets its own. Yours is a sphere 46.5 billion light-years in radius, with you exactly at the middle. So is mine. So is the one belonging to a hypothetical astronomer in a galaxy 1 billion light-years from here. Their sphere is the same size as ours, offset by 1 billion light-years, overlapping ours almost entirely but not quite. Theirs includes regions that are invisible to us. Ours includes regions invisible to them. Neither is the universe. Both are just the part of it that has had time to become visible from a particular chair. This is why the question, where is the centre of the universe, has such a maddening answer. The honest response is that there is no centre. The expansion has no origin point, no location where it all started, because it started everywhere at once. But the equally honest response, and the more useful one, is that everywhere is the centre. Every observer in the universe sits at the exact middle of their own observable sphere, sees everything receding from them in all directions, and would be entirely justified in concluding that they are at the centre of the whole thing. You are always at the centre. Remember that phrase. It sounds at the moment like a piece of pleasant cosmic trivia. By the end of tonight, it is going to be the reason the journey is impossible. The second thing that falls out is that the view from out there is not what anyone pictures. We tend to imagine that the galaxies near our horizon are somehow at the fringe, that if you went there, the universe would start to thin out, that you would see empty space on one side and everything else on the other, that you would be standing at the last house on the street. Let me take you there. You're standing on a world in the region that we currently see as Mom Z14, and it is not 280 million years after the beginning anymore. It is now. 13.5 billion years have passed for that patch of the universe, exactly as they have for ours. Whatever that young galaxy was, it has merged and settled and grown into something with spiral arms or an elliptical bulge, with generations of dead stars in it, with planets, with rock and water, and possibly with somebody standing on it looking up. And the sky above them is full, not thinning, not emptying out toward one side. There is no direction they can turn in which the galaxies run out and a boundary begins. In every direction they look, the sky is exactly as crowded as ours, with the same faint distant smudges, the same deep fields full of 10,000 galaxies in a patch the width of a grain of sand held at arm's length. Their horizon is 46.5 billion light-years away, the same as ours, and somewhere out near the margin of their sky, one of those faint red smudges is us. Or rather, it is the knot of gas that would eventually collapse into our galaxy, seen as it was in the first few 100 million years, with no sun in it, and no Earth, and nobody looking back. They are at their edge of the universe. We are at their edge of the universe. Both statements are true and neither one means anything about the universe itself. Which brings us to the third consequence, and this is the one that quietly removes the ground from under the whole question. If you set off toward the edge, genuinely set off, at any speed you like, for as long as you like, you cannot arrive. Not because it is too far, because there is no arrival event. There is nothing there to reach. The edge of the universe is not a place you have failed to get to. It is a place that does not exist as a place, in the same way that the horizon on the ocean is not a location you can visit. You can sail toward it your entire life. You will never find yourself standing on it, because it is not made of anything. It is the shape of your own vantage point, and it moves with you. Everyone gets one. They are all the same size. None of them is anywhere. There is a historical irony buried in this that I have never quite got over. The entire arc of astronomy since Copernicus has been a steady demotion. The Earth is not the centre of the solar system. The Sun is not the centre of the galaxy. We sit about 2/3 of the way out in an unremarkable spiral arm. The galaxy is not the centre of anything either. It is one of hundreds of billions, in a group of 80 or so, on the outskirts of a flow pattern that has no middle. Every century of careful measurement has moved us further from the middle of things, and the lesson everybody draws from it is that we are not special and not central, and then cosmology, working from exactly that principle, arrives at the conclusion that every single observer in the universe is at the exact centre of everything they can see. Not approximately, exactly. The demotion runs so completely to its conclusion that it turns over and hands the centre back to everyone at once. It is also worth being clear about what the boundary looks like from the inside, because horizon suggests a line, and there is no line. Objects do not blink out at 46.5 billion light-years. They fade. Their light stretches further into the infrared, and then into the microwave, and then into wavelengths no instrument will ever be built long enough to catch, and their brightness drops away as the fourth power of the stretching factor, so that a galaxy at redshift 14 is dimmed by something like 50,000 times, purely by the expansion. It is a gradual, continuous surrender, and there is no last object and no first empty patch. Sit with that for a moment, because most people carry a picture of the edge of the universe from childhood. Some final boundary, some outermost thing, a place where the universe stops and something else begins, or nothing does. That picture takes about 10 seconds to remove, and once removed, does not come back. The universe does not have an outer wall that we are too slow to reach. It has a viewing radius that belongs to the viewer. And I want to be careful here, because there is a version of this that overstates the case. None of this means the universe is only 46.5 billion light-years across. That is the observable part, the part that has had time to send us word. The universe as a whole may be enormously larger. It may be infinite. Measurements of the geometry of space, from the same cosmic microwave background data that gives us the age, come out flat to within about 2 parts in 1,000. And a flat universe in the simplest reading is one that goes on forever. If instead it curves gently closed, like the surface of an unimaginably large sphere, the data say that sphere has to be at least hundreds of times bigger than the part we can see. So there is almost certainly more out there, very probably far more, and we have measured, to a precision of a few percent, exactly how much of it we will never be able to say anything about at all. That is where the question in the title should end, and in most tellings it does. No destination, no journey, case closed. Except it does not end there, and this is the part that makes the whole subject worth 2 hours of your evening. Because while we were busy discovering that the edge is not a place, the accelerating expansion was drawing a completely different boundary in the sky. A real one, a hard one, a line with genuine physical consequences on either side of it. It is much closer than the edge. It has nothing to do with what we can see, and we crossed to the wrong side of it long before anybody knew it was there. In 1956, a physicist named Wolfgang Rindler published a paper in the monthly notices of the Royal Astronomical Society with the modest title, Visual Horizons in World Models. It is not a famous paper. It does not appear on lists of the great papers of the 20th century. Almost nobody outside cosmology has heard of it. It is also the paper that makes it possible to say anything precise at all about the edge of the universe, because it is the paper that noticed there is more than one edge and that people were confusing them. Rindler's observation was that the words being used loosely, horizon, boundary, limit, edge, We're describing at least two completely different things pointing in opposite directions in time. One was a statement about the past, the other was a statement about the future. They had different values, different behavior, and different meanings, and treating them as the same thing was generating nonsense. 70 years later, popular accounts still merge them, which is why this next stretch matters more than it looks. There are 4 boundaries commonly discussed. Only one of them is a genuine wall, and it is not the one anybody talks about. Boundary 1 is the Hubble sphere, 14.4 billion light-years out, the distance at which recession equals light speed. We met it in the last part. It is the most frequently misdescribed boundary in all of popular astronomy because it sounds like it should be a wall, and it is nothing of the sort. Objects cross it in both directions. Photons pass through it inbound all the time. It grows as the universe ages. It marks nothing except the place where one particular arithmetic quantity equals one particular other quantity. Cross it off. Not a wall. Boundary 2 is the particle horizon, 46.5 billion light-years, the one we have been calling the edge. It is a statement about the past, the furthest moving distance from which light emitted at any point in the history of the universe could have reached us by now. It is real in the sense that it genuinely limits what we can see. But it is not a wall either, because it is growing. Every year that passes, light from a little further out finishes its journey and arrives, and the observable universe gets bigger. It has been getting bigger since the moment the universe became transparent, and it is bigger tonight than it was last night. A boundary that retreats every time you wait is not a wall. It is a delay. Boundary 3 is where it gets serious. This is the cosmological event horizon, and it is a statement about the future. Here is the definition, and it is worth hearing slowly. The cosmological event horizon is the maximum distance a signal emitted right now could ever reach. Not by next year, not by the end of the century, but ever. Integrated forward over infinite time. If you fire a laser into space tonight and let it travel for all of eternity, there is a finite sphere it will eventually fill, and there is everything outside that sphere, which it will never touch. The radius of that sphere is about 16.7 billion light-years, and because the geometry is symmetric, the statement runs both ways. Anything beyond 16.7 billion light-years that emits a signal tonight is emitting a signal that will never reach us. Not late, never. There is no amount of patience that fixes it. It helps to make that concrete with something small. Suppose that tonight, for reasons of your own, you build a transmitter and send a message. A simple one, a greeting, whatever you like. And you aim it at a particular galaxy in a deep field image. If that galaxy is closer than 16.7 billion light-years, your message is on its way. It will take an absurd length of time. It will arrive weakened almost past recognition. But there exists a moment in the future at which it lands, and the universe contains a causal path from your evening to that arrival. If the galaxy is beyond 16.7 billion light-years, no such moment exists. Your message departs, travels forever at the speed of light, and never arrives. And this is not a matter of the signal getting too faint or the receiver going out of business. The path itself is not there. You can see the galaxy on your screen while you type. You can measure its spectrum, and there is nothing you can do, at any point in the entire remaining future of the universe, that will ever have the slightest effect on it. Rindler, incidentally, has a second horizon named after him, and the pairing is instructive. A Rindler horizon is what an observer feels when they accelerate steadily through ordinary flat space-time. Behind them, at a fixed distance, there forms a surface from which light can never catch up. Just keep accelerating and part of the universe falls permanently behind you. It is the closest everyday analogue to what dark energy is doing to us, except that we are not the ones accelerating, and there is no engine to switch off. Boundary 4, for completeness, is what you get when you add the first two of those together, the ultimate particle horizon, at about 62 or 63 billion light-years. That is the absolute limit of what will ever become visible from here, no matter how long the universe or its observers last. The observable universe will keep growing toward it and will never exceed it. Everything beyond 62 billion light-years is not merely invisible tonight. It is permanently and structurally unknowable, and its existence is a mathematical inference rather than an observation. So, 4 boundaries. One that is not a boundary at all, one that grows, one that is a hard limit on the future, and one that is a hard limit on eventual knowledge. Now here is the fact that should stop you, and it is the reason the last several minutes have been worth spending. The particle horizon is 46.5 billion light-years. The event horizon is 16.7 billion light-years. The thing we can see is nearly 3 times bigger than the thing we can touch. Take a moment on that, because it is deeply counterintuitive and there is nothing in ordinary life that prepares you for it. Everywhere else in your experience, the range of what you can perceive is a subset of the range of what you can affect, or at worst, roughly comparable. You can see the far side of a valley and you can walk there. You can see an aeroplane and, given a phone and enough determination, you could contact someone on it. Perception and reach are not identical, but they are in the same family. Out here they come apart by a factor of nearly 3 in radius, which is a factor of about 20 in volume. The universe is arranged so that we are shown enormously more than we are given. And it did not have to be that way. This is the part that makes it feel less like geometry and more like a decision somebody made. In a universe containing only matter, no dark energy, gravity slowly winning, the expansion decelerating forever, there is no cosmological event horizon at all. None. The reachable region grows without limit. Wait long enough, and any 2 points in the universe can exchange a signal. It might take 100 billion years, it might take 100 trillion, but there is no permanent separation anywhere. Everything eventually connects to everything. That is the universe almost every cosmologist believed we lived in until 1998. Dark energy is what puts the wall up. Because the expansion is accelerating, distant regions are not merely receding. The rate at which they recede is increasing. A photon fired at a target 16.7 billion light-years away is chasing something that is speeding up, and it loses that race by an arbitrarily large margin over infinite time. Beyond that radius, the gap opens faster than light closes it, forever, and no amount of waiting turns it around. The acceleration did not just change the fate of the universe in some distant abstract sense, it fenced it. There is one more feature of this boundary that makes it genuinely unlike anything else in physics, and it is the thing I find hardest to shake. It is invisible, completely. A black hole's event horizon at least has a location. You could in principle fly out and mark it, put a beacon there, watch things fall past it. The cosmological event horizon has no such thing. There is nothing at 16.7 billion light-years, no object, no boundary, no change in the density of galaxies, no shift in the physics, no signal of any kind. If you flew to it, supposing for the moment that you could, you would find ordinary space with ordinary galaxies in it, and your own event horizon would have moved with you, and the boundary you came to find would be 16.7 billion light-years further on. There is a further wrinkle that physicists find beautiful, and that most people never hear about. Mathematically, the cosmological event horizon behaves a great deal like the event horizon of a black hole. Both are surfaces past which signals cannot return. Both have an entropy associated with them that is proportional to their area rather than to any volume. And both have a temperature. The cosmological horizon glows very faintly, with radiation associated with the horizon itself, at something on the order of 10 to the minus 29 degrees above absolute zero. That is not a temperature anyone will ever measure. It is colder than anything, by an amount that makes the word colder feel inadequate. But it is not zero, and the fact that it is not zero is a hint that horizons in general, the ones around collapsed stars and the one around all of us, are the same kind of object, and that we do not fully understand what kind of object that is. As the dark energy comes to dominate more and more completely, the universe settles toward a state that has been studied since the 1920s, a smooth, exponentially expanding space with a horizon of fixed size and nothing else in it. Everything currently in the sky either falls into our local gravitationally bound group or crosses that horizon and is gone. The endpoint is a single island of stars sitting inside a fixed bubble about 16 billion light-years across, and outside it, as far as anything inside can ever determine, nothing at all. It is not a place, it is a relationship between two places, and unlike the particle horizon, which merely means we have not heard from them yet, this one means something absolute and final about what can ever pass between here and there. So the next question is the obvious and unpleasant one. 16.7 billion light-years is a long way. Almost everything we care about, everything with a name, everything in every photograph is closer than that, isn't it? 16.7 billion light-years sounds generous. It is more than the age of the universe expressed in light-years. It is far beyond anything with a name. So let us find out where it actually falls in the sky. And the way to do that is to convert it from a distance into a redshift, because redshift is what astronomers actually measure. The answer is redshift 1.6, possibly 1.7, depending on exactly which values you use for the expansion rate and the dark energy density. Call it 1.6 and hold the uncertainty in mind. That is the line. Everything in the sky with a redshift below about 1.6 is, in principle, still reachable. A signal sent tonight can get there. A ship sent tonight could in principle arrive. Everything with a redshift above 1.6 is gone. Permanently, structurally gone, in the sense that nothing we do from this moment forward can ever reach it or affect it in any way. The calculation that establishes this properly was published by the astrophysicist Abraham Loeb in 2002 in Physical Review D under the deliberately dry title The Long-Term Future of Extragalactic Astronomy. It is 4 pages long. It is one of the most quietly devastating papers in modern cosmology, and almost nobody outside the field has read it. Now let us work out what redshift 1.6 actually means for the sky you can look at tonight. In terms of look-back time, redshift 1.6 corresponds to light that left its source about 9.5 billion years ago. The universe was roughly 4 billion years old. Our sun did not exist and would not for another 5 billion years. So the rule of thumb, and it is a good one, is this. Anything you can see whose light is older than about 9.5 billion years is beyond reach. That does not sound like much of the sky until you go and look at what is actually in the sky. Nearly every galaxy in the famous deep field images is past it. When astronomers point a large telescope at an apparently empty patch of sky and leave the shutter open for days, the thousands of galaxies that emerge are overwhelmingly at redshifts of 2, 3, 5, 8, and beyond. That is the entire point of the exercise. You take a long exposure specifically to catch the faint, distant, early things. Almost every galaxy and every deep field poster is on the far side of the line. The great majority of known quasars are past it, since quasar activity peaked around redshift 2. Every galaxy that the James Webb Space Telescope has been celebrated for finding, the early ones, the surprisingly massive ones, the record breakers at redshift 11 and 14, is not merely past the line. It is past it by an enormous margin. Now do the volumes, because that is where the number that matters comes from. The reachable sphere has a radius of 16.7 billion light-years. The observable sphere has a radius of 46.5. The ratio of the radii is about 0.36. Volume scales as the cube of radius, so the ratio of the volumes is 0.36 cubed, which is about 0.046. Roughly 4.5%. About 4.5% of the volume of the observable universe is, even in principle, reachable, which means about 95% of it is not. And if the galaxies are spread out reasonably evenly at these scales, which every large survey says they are, then about 95% of the galaxies you can see tonight are permanently out of reach. Not out of reach of our engines, out of reach of light, emitted tonight, given eternity. Convert that into a count and the number gets hard to hold. If there are 2 trillion galaxies in the observable universe, then something like 100 billion of them remain reachable, and something like 1900 billion do not. If the lower estimate is right, and there are only a few 100 billion galaxies in total, the reachable number drops to something in the low tens of billions. Either way, the reachable population is enormous in absolute terms and small as a fraction, and either way the fraction is the part that matters, because the fraction is a fact about geometry, while the absolute number is a fact about how many galaxies happen to form. It also helps to name specific things on each side of the line, because percentages slide off. The Sombrero Galaxy, 28 million light-years away, and one of the most photographed objects in the sky, reachable, comfortably, with room to spare. The Virgo cluster at 54 million light-years, reachable. The Coma cluster at 320 million, reachable. The great sheets and filaments of galaxies mapped out to 1 billion light-years and beyond in the big redshift surveys, still, remarkably, reachable. You have to go out past 9.5 billion years of look-back time before the line bites, and that leaves an extraordinary amount of universe on the near side of it. And then there is everything else. Every quasar in the peak era of quasars, every galaxy in the Hubble Ultra Deep Field, which is the single most information-dense photograph ever taken, and shows a patch of sky about a 13 millionth of the whole. every object Webb was built to find, all of it on the far side, the entire early universe, the entire period during which galaxies were assembling, the whole formative history of everything, visible in extraordinary detail and permanently untouchable. I want to be precise about the strength of that claim, because it is easy to hear it as a version of the usual complaint that space is big and rockets are slow. It is not that. There is no technology that fixes this, because it is not a technological limitation. It would not be fixed by a fusion drive, or by antimatter, or by a civilization with 1 billion years of engineering behind it. The fastest possible thing in the universe, launched tonight, with unlimited energy and perfect efficiency, does not arrive. The path does not exist. And here is the part that I have never been able to make peace with. Nothing happens when a galaxy crosses that line. There is no event, no flash, no fade, no shudder in the data. A galaxy that crosses out of the reachable universe tonight will look precisely the same tomorrow as it did yesterday. Its spectrum will be unchanged. Its brightness will be unchanged. Every measurement anyone makes of it will be exactly what it was the day before. There is no observational signature of any kind at the moment of crossing or afterward, and it is entirely possible, it is in fact certain, that this has been happening continuously throughout the entire history of astronomy, without anyone noticing, because there is nothing to notice. The light is still arriving. I said in an earlier part that this phrase was the reassuring part of the story. Here is where it stops being reassuring. Tonight, right now, photons are landing on telescope mirrors around the world, from galaxies that we can never reach and that can never reach us. That light left them billions of years ago, when a connection was still possible. It has been in transit ever since. It will keep arriving for billions more years, dimming, reddening, thinning out, but arriving. Astronomers will keep photographing those galaxies for longer than the sun has left to burn, and every single one of those photographs is of a correspondence that has already ended. The light is a letter posted before the sender moved away without a forwarding address. It keeps coming. It is real. It is beautiful. There is nothing on the other end of it anymore, in any sense that would let you send a reply. There is a particular quality to that which I think is worth naming honestly rather than dressing up. It is not loss in the way an extinction is a loss, or a death. Nothing has been destroyed. Those galaxies are all still there, still turning, still making stars, still perfectly fine. Whatever is happening in them is happening. It is more like the feeling of watching a ship leave harbour and knowing, while you can still make out people on the deck, that you will never speak to any of them again, and knowing it while they are still clearly visible, still waving, still entirely present in your field of view. The sky is full of light from places that are already gone, and the sky does not look any different for it. There is no way to tell from the picture which of those galaxies you could still shout at, and which of them have already stopped being able to hear, and it is still going on. The reachable sphere is not a fixed inventory that was settled long ago. Its co-moving radius shrinks continuously, and galaxies drop out of it one by one, the way water leaves a bath. The exact rate depends on the galaxy counts and therefore inherits that factor of 10 uncertainty. But the order of magnitude is not in doubt. Over a human lifetime, a number of galaxies comfortably in the millions has passed from the column marked reachable to the column marked gone. Not a single one of those crossings was observed, because there was nothing to observe. Somewhere in the sky above you tonight there are galaxies making that transition while you listen to this, and they will look exactly the same in the morning. There is one more detail here, and it is the strangest of all, because it makes the parallel with a black hole exact. Because the expansion is accelerating, a galaxy beyond our event horizon does not just recede. Its light reaches us from later and later moments in its own history more and more slowly. Its clock, as we see it, runs down. The light gets redder without limit, and there is a specific moment in that galaxy's own history, a specific tick of its own clock, whose light we will approach seeing and never quite receive, no matter how long we watch. Everything before that moment reaches us eventually. Nothing after it ever does. Every galaxy beyond the horizon has a final frame from our point of view. Not a moment when it ends, because it does not end. It goes on for billions of years having an ordinary galactic existence, forming stars and merging and doing all of it in full view of its own neighbours. But there is a last moment of it that will ever be shown to us, and we will spend the rest of the universe's history creeping asymptotically toward that frame without reaching it, watching the same increasingly reddened image slow down forever. We have not been cut off. We are being cut off, continuously, in an extremely slow and completely silent way, and the process began long before anyone worked out that it was happening. That is the honest picture, and I am aware it is a heavy one to sit with at this point in the evening, so let us step back, because it is not the whole picture, and the part I have not told you yet is the part with the good news in it. We are about halfway through, so let us stop and put the pieces together before going on, because a few of them have been set down in different places and they make a shape. Here is where we have got to. The universe is 13.8 billion years old, and the furthest thing we can see is 46.5 billion light-years away. And that is not a contradiction, because space itself has been stretching underneath the light the whole time it has been travelling. That stretching is why distant galaxies recede, why the light from them arrives reddened, and why anything past redshift 1.5 is receding faster than light without breaking any rule, because it is not moving. The distance is growing. The edge of what we can see is not a wall or an object. It is the surface at which look-back time equals the age of the universe. It is centered on whoever is doing the looking, and every observer in the universe has one exactly the same size as ours. There is nothing at it. Going there would simply relocate it. But underneath that, drawn by the accelerating expansion, there is a second boundary that is a genuine wall. The cosmological event horizon at about 16.7 billion light-years, past which nothing we send tonight can ever arrive. It corresponds to about redshift 1.6, or roughly 9.5 billion years of look-back time. Around 95% of what we can see is on the far side of it, and its crossing is completely silent. That is the picture. Now here is the part of it that is genuinely good, and I have been holding it back deliberately, because it deserves a clean stretch of its own. Not everything goes. Dark energy is remorseless, but it is also, on small scales, extremely weak. It only wins where there is enough distance for it to accumulate. Where gravity has already pulled a structure together tightly enough, the expansion loses, permanently, and that structure simply drops out of the whole conversation. It stops participating in the expansion of the universe. It is not stretching. It never will. The Earth is not expanding. The solar system is not expanding. The Milky Way is not expanding. It is a bound structure 100,000 light-years across, held by its own gravity, and it will still be 100,000 light-years across when the last star in the observable universe outside our own group has vanished. And crucially, the local group is not expanding either. The local group is the collection of galaxies that our galaxy actually belongs to. Two large spirals, the Milky Way and Andromeda, plus the somewhat smaller Triangulum galaxy, plus something like 80 smaller companions, satellites and dwarfs, some of them so faint they were only catalogued in the last 20 years. It is roughly 10 million light-years across, and has a total mass on the order of 2 trillion suns, and it is gravitationally bound, which means all of it stays. Andromeda is 2.5 million light-years away, and it is not receding at all. It is approaching at about 110 kilometers per second. It has been approaching for billions of years, and dark energy has not made the slightest difference to it, because 2.5 million light-years is simply not enough distance for the expansion to accumulate against gravity that strong. The textbook date for the collision is about 4.5 billion years from now, and it is worth putting a small honest asterisk on that, because it has softened recently. Measuring how fast Andromeda is moving toward us is comparatively easy. You read it straight off the spectrum. Measuring how fast it is moving sideways is extremely hard, and sideways motion is what determines whether two galaxies collide or sail past each other. The Gaia spacecraft has been chipping away at exactly that measurement, and work published in 2024 brought the probability of a merger within the next 10 billion years down to something closer to a coin flip than a certainty. Likely, still. Guaranteed, no longer. If it does happen, the two spirals will pass through each other, tear each other's arms apart, and settle over 1 billion years or so into a single large elliptical galaxy. Almost no stars will collide. The distances between them are so enormous that two galaxies passing through one another is more like two clouds of gnats meeting than two walls colliding. Whatever is orbiting the Sun by then will most likely go through the entire event without anything happening locally except a changed sky. That merged object is where our entire future lies, and it is permanent. It does not disperse. It does not redshift away. In 100 billion years, when every other galaxy in the observable universe has crossed the horizon or faded past detection, It will still be there, still making stars out of its own recycled material, still gravitationally bound, still ours. 10 million light-years on a sky 46.5 billion light-years across. That is the fraction of the universe that is permanently, unconditionally ours. It is not nothing. It is the difference between a future and no future at all. But the proportion is worth stating plainly, because the honest version of the good news is that we get to keep the room we are standing in. Astronomers have a nickname for the merged remnant, which is Milkomeda, and I have never been able to decide whether it is charming or slightly undignified for the last thing that will ever be ours. There is a clean physical criterion behind all of this, and it is worth having, because it tells you exactly which structures survive. For any collection of matter there is a radius, sometimes called the turnaround radius, inside which gravity is strong enough to have pulled material back rather than let it join the general expansion. Inside that radius, the structure collapses and binds. Outside it, everything is on its way out and always was. For a group with the mass of the local group, that radius works out to something in the region of a few million light-years, which is why the local group binds and why Virgo, sitting 54 million light-years off, does not and never did. The boundary between what you keep and what you lose is not a matter of degree or of waiting long enough. It was fixed by the mass of the group and the density of dark energy, and it was fixed billions of years ago. It is also not simply a matter of being pulled. We are being pushed. On the opposite side of the sky from Virgo sits the local void, an enormous underdense region roughly 150 to 300 million light-years across with very little in it, and because there is less matter there than average, its net gravitational effect is to push us away from it, a repeller rather than an attractor. A good fraction of our motion through the universe is the local void quietly getting rid of us. Our galaxy is being simultaneously pulled toward the crowded parts of the sky and evicted from the empty ones, and neither influence will make the slightest difference to what we end up keeping. Now, between permanently bound to us and permanently unreachable, there is a large middle category, and this is where the answer to tonight's question actually lives. The Virgo cluster, at about 54 million light-years, is not bound to us. The local group is not going to fall into it. Dark energy settled that question some time ago, and the two will simply drift apart. But Virgo is comfortably inside the event horizon. A signal sent tonight arrives. A ship sent tonight, at a sufficient fraction of light speed, arrives. The same is true of the Coma cluster at 320 million light-years, and of the Great Attractor at about 250 million, and of the enormous flow pattern of 100,000 galaxies called Laniakea that our galaxy technically belongs to, 520 million light-years across, which is not a bound structure and will come apart, and which is nonetheless entirely inside the reachable sphere. So the honest accounting of the situation looks like this. There is a small permanent home, 10 million light-years across. There is a large reachable region extending out to 9.5 billion years of look-back time, containing somewhere in the tens of billions of galaxies, every one of which could in principle be visited by something launched from here. And there is everything else, which is most of it, and which is closed. Tens of billions of galaxies is not a consolation prize. It is more places than any civilization could catalogue, let alone occupy, in a length of time that makes the age of the Earth look brief. On the geometry alone, the door is not shut. It is narrow relative to the sky, and it is enormously wide relative to any ambition anyone has ever had. Which leaves exactly one question standing between us and an answer. Everything I have just said about the reachable region assumes a ship travelling at a serious fraction of the speed of light, not 1%, not 10, something up against the limit, closing the distance almost as fast as light itself, because anything slower is racing an expansion that never gets tired. So it is time to find out what that actually costs, not in the abstract, in joules, in tons of fuel, and in what happens to the front of a ship moving that fast through what turns out to be the emptiest place in creation. Set the horizon aside completely for a while. Pretend it does not exist. Suppose the universe were the friendly, decelerating kind that everyone believed in before 1998, with no wall anywhere and everything eventually reachable. What would it actually cost to cross intergalactic space? This is worth doing carefully, because intergalactic travel is not interstellar travel scaled up. It is a different problem with different terms dominating, and several of the things you would expect to be dangerous turn out to be harmless, while several things you would expect to be harmless turn out to be the whole difficulty. Start with the energy, because it is the least forgiving number in the entire subject. To reach 99% of the speed of light, you need to give an object about 6 times its own rest energy. That comes out of the relativistic energy relation, and there is nothing you can do about it. At 99% of light speed, the factor by which everything about a moving object is distorted is a little over 7, and the kinetic energy you have had to supply is that factor minus 1, multiplied by the mass, multiplied by the speed of light squared. For a single kilogram, that is about 550 quadrillion joules. 5.5 times 10 to the 17. Now build a ship. Not a colony vessel, not a generation ship, nothing ambitious, 1,000 tons, which is roughly 2.5 times the mass of the International Space Station, and a very modest object to send between galaxies. It needs about 5.5 times 10 to the 23 joules to reach 99% of light speed. Total human primary energy consumption, everything, all fuels, all electricity, the whole planet, runs at around 6 times 10 to the 20 joules per year. So the acceleration alone costs a little over 900 years of total human energy production. All of it, with nothing left over for anything else, at 100% conversion efficiency with no losses anywhere, which is not a thing that exists, and you have to pay it twice. That is the detail people forget, and it is the one that turns a hard problem into an impossible one. You cannot arrive at 99% of light speed. You have to slow down. A flyby of a galaxy you spent 10 billion years reaching is not a journey, it is a photograph. You would cross the entire disk in a few 100,000 years of instrument time and be gone, having sent back one increasingly redshifted data burst. To actually arrive, you have to shed all of that velocity, which costs the same again. 18 centuries of planetary energy output minimum for 1,000 tons. Then there is the propellant, and here the physics is even less negotiable. The absolute theoretical ceiling of rocketry is a photon rocket. Perfect matter-antimatter annihilation, everything converted to light, exhaust leaving at the speed of light itself. Nothing can do better, because nothing can be thrown backwards faster than that. For that ideal engine, reaching 99% of light speed requires a mass ratio of about 14. 14 kilograms of fuel and structure for every kilogram that arrives, and because you have to decelerate, you square it. About 199 to 1, so your 1,000-ton ship needs 200,000 tons of fuel, and it needs half of that to be antimatter, and antimatter is currently produced in quantities measured in nanograms per year, at a cost that makes gold look like sand. Every real propulsion concept anyone has ever drawn is worse than this, by many orders of magnitude, because none of them convert mass to energy perfectly. This is not the engineering target. This is the wall the engineering targets are trying to approach from below. 2 escape routes have been proposed from that mass ratio, and both close. The first is to stop carrying the fuel and scoop it up instead. Robert Bussard suggested in 1960 that a ship could spread an enormous magnetic funnel ahead of itself, gather interstellar hydrogen as it went, and fuse it for thrust, an engine that gets more efficient the faster it goes, with no propellant tank at all. It is one of the most elegant ideas in the history of spaceflight, and it does not work. Later analysis, principally by Robert Zubrin and Dana Andrews, showed that the drag exerted by the magnetic scoop on the medium it is collecting exceeds the thrust it can generate from that medium. The engine is a brake, and for our purposes the point is academic anyway, because intergalactic space has 1 atom per cubic meter, and there is nothing out there to scoop. The second is to leave the power plant at home, build an enormous laser array in your own solar system, aim it at a light sail, and push the ship without it having to carry anything. This one genuinely works, and it is the basis of every serious near-term interstellar concept anyone has funded. It also has a fatal asymmetry. The laser is behind you. It can accelerate you beautifully, and it cannot slow you down. Every beamed sail proposal ends with a flyby, because nobody has solved the problem of decelerating at a destination where you have not yet built anything. And I should say something about the energy figure itself, because there is a version of this argument that overstates the case, and I do not want to make it. 900 years of human energy production sounds final. It is not, if you are patient and ambitious. The sun radiates about 3.8 times 10 to the 26 watts in every direction at once, of which the Earth intercepts roughly a 2/1000th. A civilization that captured even a modest fraction of its own star's total output would generate that 900 years of human energy in a matter of seconds. The energy required for relativistic intergalactic travel is not a physical impossibility. It is a very long way beyond us, and it is comfortably within reach of a civilization that has learned to live off its star rather than off a planet. That is worth being clear about, because it means the energy is not the reason the answer to tonight's question is what it is. Somebody could pay this bill. The bill is not what stops them. Now, for the part that inverts the intuition, you would expect that moving at 99% of light speed through the universe would be lethal, and that the emptiness between galaxies would be the most dangerous place of all. It is exactly the opposite. Interstellar space, inside a galaxy, contains roughly 1 million hydrogen atoms per cubic meter. Intergalactic space contains something on the order of 1. It is a million-fold improvement, and it is the emptiest environment that exists anywhere. At 99% of light speed, each of those solitary atoms arrives at the front of your ship as a proton carrying about 7 billion electron volts. Genuine cosmic ray energies, the sort of thing accelerator physicists build kilometers of magnets to produce. That sounds appalling. But you are sweeping up 1 atom per cubic meter, and even at 300 million meters per second, the total power deposited on the forward hull works out to a fraction of a watt per square meter. Less than standing in sunlight. Roughly the warmth of a candle across a whole wall. The emptiest place in the universe is, by an enormous margin, the safest place to travel fast. Every serious hazard in relativistic flight is a hazard of leaving or arriving, of crossing the crowded disk of a galaxy at either end. The 10 billion light-years in between are the easy part, except for one thing, and this one scales viciously. The cosmic microwave background is everywhere. It fills all of space uniformly in every direction, at 2.725 degrees above absolute zero, the coldest thing in the universe and the most thoroughly distributed. And when you move through it, it stops being uniform. The photons coming from ahead are blue-shifted, the ones from behind are red-shifted. The sky in front of you gets hotter simply because you are moving toward it. At 99% of light speed, the forward blue shift factor is about 14. The relic radiation ahead of you arrives as though it were coming from something at 38 degrees above absolute zero rather than 2.7. That is still ferociously cold. It is still harmless. It amounts to about 1/10 of a watt per square meter, which you would not notice. Push harder, though, and the arithmetic turns on you. At a factor of 1,000, which is where you need to be if you want the ship's own clock to compress 10 billion years down to something a crew could live through, the blue shift factor is about 2,000. The forward sky arrives at around 5,400 degrees, which is the surface temperature of the sun, and radiated power goes as the fourth power of temperature, so the flux climbs to tens of kilowatts on every square meter of the leading surface. The coldest, gentlest, most uniform thing in the universe becomes a wall of light hotter than a stellar surface, purely and entirely because you are moving toward it, not from any object, from the background itself. The faster you go, the more the universe glows. Let me put you on the bridge. You're aboard, at 99% of light speed, 10 million light-years out from anywhere, and the first thing you would notice is that the sky is wrong. The stars have moved. Not slightly. Everything has crowded forward. Light arriving from the sides is swept toward the bow by the same effect that tilts rain onto a windscreen, so the entire sky compresses into a brilliant ring ahead of you and thins to almost nothing behind. There is a bright, tight aperture forward, and behind you an emptiness widening by the year. And it is not that the stars have gone out. It is that the direction they are in has changed. The forward light is bluer than it should be, all of it. Every galaxy shifted up the spectrum by a factor of 14. The dim ones ahead have brightened. The ones behind have reddened past seeing. On the instruments there is a faint reading from the whole forward hemisphere at 38 degrees above absolute zero, coming from nothing, from the background, from the leftover heat of the beginning of everything, arriving warmed by your own motion, and there is no sensation, no wind, no vibration, no sense of speed at all. Outside the hull, roughly 1 hydrogen atom per cubic meter is striking you at 7 billion electron volts, and the hull is barely warming. It is the quietest, emptiest, calmest environment any traveller could ask for. It is also the most expensive journey imaginable, and even at 99% of light speed and 18 centuries of planetary energy, you're still going to lose. Because there is a second bill, and it is not paid in joules. It is paid in something nobody can borrow, and it comes due the moment you arrive. There is exactly one term in this whole accounting that works in the traveller's favour, and it works so spectacularly well that it has misled generations of people about how difficult the problem actually is. That term is time dilation. When you move very fast, your own clock runs slow relative to everyone you left behind. This is not an illusion, or a matter of perspective, or a trick of measurement. It has been confirmed to extraordinary precision with atomic clocks flown around the world, with muons produced in the upper atmosphere that reach the ground when they have no business surviving the trip, with particles held in accelerator storage rings living dozens of times longer than they should, and with the satellites overhead right now, whose clocks have to be corrected by tens of microseconds a day, or the navigation would drift by kilometers. Time dilation is real, it is routine, and for interstellar and intergalactic travel it does something remarkable. None of that is theoretical. Clocks flown east and west around the world in 1971 came back disagreeing with the clock left at home in both directions by exactly the predicted amounts. Tens of nanoseconds, but exactly the right tens of nanoseconds. Muons created high in the atmosphere by cosmic rays live about 2/millionths of a second in the laboratory, and should decay long before reaching the ground, and they reach the ground in quantity because from their point of view the trip is short. In a storage ring at CERN, muons circulating at a distortion factor of about 29 were measured living about 29 times longer. This is one of the most thoroughly verified predictions in physics, and it is boring in exactly the way a settled result should be. Suppose you build a ship that accelerates continuously at one gravity, comfortable, familiar, exactly the pull you're sitting in right now, for the first half of the journey, then turns around and decelerates at one gravity for the second half. That is the most humane trip profile imaginable. Nobody is crushed, nobody floats, everybody arrives at rest. Because the ship's clock slows as the speed builds, the distance covered per year of ship time grows without limit, and the journey time as felt by the crew stops behaving like distance and starts behaving like the logarithm of distance. Andromeda, 2.5 million light-years away, takes about 28 years of ship time. The Virgo cluster, at 54 million light-years, takes about 35, and the far edge of the observable universe, 46.5 billion light-years, takes about 48 years. Read those three numbers again, because they are absurd. Increasing the distance by a factor of about 20,000 increased the journey by 20 years. A crew that set out in their 20s would arrive at the far side of the visible universe in their 70s, having aged normally, eaten dinner every evening, and watched their children grow up on board. This is the fact that makes people optimistic about intergalactic travel, and it is entirely true, and it is entirely beside the point. Because there are two clocks. The ship's clock reads 48 years, the universe's clock does not. Outside the hull, the coordinate time elapsed is essentially the light travel time plus a bit. Tens of billions of years. The crew has aged by decades. Everything else has aged by aeons. Nobody has cheated anything. The compression is real for the people aboard, and it is not shared by anyone or anything else. Time dilation does not shorten the journey. It shortens your experience of the journey, which is a completely different commodity, and it is a commodity that is only useful to the passengers. Here is what that means when you arrive. You aimed at a galaxy because you could see it, and what you could see was 10 billion years old when it entered your telescope. You then spent another 10 billion years of universe time getting there. So the place you arrive at is 20 billion years further along its own history than the picture you set off toward. The stars in your target images are gone. Not dimmed, gone, burned through, collapsed, dispersed into gas that has already formed new stars that have themselves lived and died. The spiral structure you photographed may not exist. Spiral arms are patterns, not objects, and they wash out and reform on timescales far shorter than that. If the galaxy had companions when your light left, they have merged. If it was forming stars vigorously, the gas is likely spent. There is no way to correct for this either, and that is worth dwelling on for a second. You cannot navigate by anything except light, and light is a report from the past. Every star chart, every survey, every catalogue you carry aboard is a description of a universe that has not existed for billions of years. You are steering by a photograph and arriving in a place. The gap between the two is the length of the journey, and the journey is the reason the gap exists. You did not travel to a place. You travelled to a very much later version of a place, and there was no way to know what that version would be, because the only information you ever had about it was 10 billion years out of date before you started. Let me put you at the moment of stepping out. The ship has been decelerating for 24 years, and the stars have been sliding back out of that bright forward ring toward their proper positions all the while. Now they are still. The engine noise, whatever it was, has stopped. Outside there is a galaxy filling half the sky. It is not the one in the photographs. It is the same object in the same way that a 70-year-old is the same person as their baby picture, and about as recognizable. The color is wrong, redder, older, the blue-white glare of young massive stars long since spent. Where the survey images showed two objects, there is now one, settled and smooth. The arms are not where they were. In some directions there is no structure at all, only a spread of old stars going quietly about the business of dimming. You have aged 48 years. Everything you can see has aged 20 billion. And then someone on the crew does the obvious thing, which is to turn a transmitter around and point it home, and this is the moment the trip properly lands. The signal leaves at the speed of light. It has 10 billion light years to cross, against an expansion that has been accelerating the entire time you were travelling and has not stopped. If the target is inside the horizon, the message arrives. In another 10 or 20 or 40 billion years, at whatever is still there. If the geometry has moved against you, it does not arrive at all. Either way, nobody is waiting. The civilization that built the ship is not a thing that exists on those timescales. The species is not a thing that exists on those timescales. The star it orbited has, in all probability, finished being a star. You are transmitting to a coordinate, not to a people, and you will never learn whether anything received it. That is the second bill, and it is the one that cannot be paid with energy. You can buy the crossing. You cannot buy a receiving civilization on the far end of 20 billion years, and without one, a journey and a disappearance are the same event. There is a further twist here that I find genuinely unsettling, and it concerns when you should leave. For ordinary interstellar travel, there is a well-known argument sometimes called the weight calculation. If your technology is improving, and a ship launched 50 years from now would travel twice as fast, then leaving today is irrational. You would be overtaken en route by a vessel that had not even been built when you departed. The rational move is almost always to wait, and to keep waiting, until the rate of improvement slows. It is one of the reasons some people think interstellar expansion may be much rarer than it looks. The horizon inverts that argument completely. Waiting is not free out here. The reachable sphere is shrinking the entire time you deliberate, and every century of prudent delay permanently removes galaxies from the list of possible destinations. Not from the list of things you can see, from the list of things that exist for you in any operational sense. There is no technology arriving later that recovers them, because they were never lost to technology. So for the first time there is a genuine deadline attached to a cosmic ambition. Not a soft one, not a matter of resources or political will. A hard, silent, geometric deadline that has been running for billions of years, that produces no observable event when it passes, and that nobody in the entire history of the universe has ever received a warning about. And there is one more figure worth putting on the table before we leave this, because it quietly disposes of the one-gravity ship altogether. To keep a steady one-gravity all the way to the edge of the observable universe, the ship has to reach a distortion factor of something like 20 billion, meaning its clock runs 20 billion times slower than the universe's. Even a perfect photon rocket converting matter and antimatter to light with no losses at all would need a fuel-to-payload ratio in the region of 10 to the 21 to reach that and stop again. For a 1,000-ton ship, that is around 10 to the 24 kilograms of fuel, roughly a sixth of the mass of the Earth, half of it antimatter. So the comfortable 48-year crossing is not a plan. It is an illustration of what relativity permits and chemistry, nuclear physics and the mass of the observable universe forbid. Which leaves one door, and it is the door every story reaches for at exactly this point. If the problem is that light is too slow, and everything about this is bounded by the speed of light, then the answer is obvious. Go faster than light. It is worth finding out what that would actually buy you, because the answer is not what anybody expects. Everything we have established so far has been bounded by one number. The speed of light limits how fast a ship can cross a gap. It limits how fast a signal can chase a receding galaxy. It is the thing the expansion is outrunning when it draws the event horizon. Take it away, and on the face of it, the entire problem evaporates. So let us take it away. The most serious version of this idea was published in 1994 by a Mexican theoretical physicist named Miguel Alcubierre in the journal Classical and Quantum Gravity, and it is a genuinely clever piece of work rather than a piece of fiction. His starting point was the observation we have been circling all evening. General relativity places no limit whatsoever on how fast space itself can expand or contract. Only objects moving through space are bound by the speed of light. Space has no such restriction, and we have the entire observable universe as evidence. So, he asked, what if a ship did not move through space at all? The Alcubierre solution describes a bubble of flat, ordinary space-time with the ship sitting quietly inside it, not moving, not accelerating, feeling nothing. Ahead of the bubble, space contracts. Behind it, space expands. The bubble is carried along by that contraction and expansion, the way a surfer is carried by a wave. The surfer is not swimming, and the wave is not bound by how fast a person can swim. Inside the bubble, the ship never exceeds the speed of light relative to its immediate surroundings. Relativity is not violated anywhere locally, and the bubble as a whole can move between 2 points faster than light could travel between them. It works, in the sense that it is a genuine solution to Einstein's field equations. It is in the literature. You can look it up. The problems are considerable, and I will not pretend otherwise. The geometry requires a region of negative energy density, matter with in effect negative mass, which nothing in the observed universe has ever been found to possess. The quantities involved in the original formulation were on the scale of the mass of Jupiter, converted entirely into negative energy, and later work has both reduced and complicated that estimate. There are quantum inequalities that constrain how much negative energy can be concentrated in one place, and for how long. There is a horizon problem inside the bubble itself, which means the ship at the centre cannot send a signal to the leading edge to steer it or switch it off. And Stephen Hawking argued in 1992 that the laws of physics conspire to prevent exactly this sort of thing, because anything that lets you travel faster than light also lets you, with the right arrangement of motion, arrive before you departed. The honest state of the field, as of tonight, is that serious work has continued and has been moving in an interesting direction. Papers published in 2021 and again in 2024 have constructed warp-drive geometries that require no negative energy at all and satisfy every energy condition general relativity asks for. They are real, they are respectable, and they are strictly slower than light. The exotic requirements turn out to be attached specifically to the superluminal part. Remove the demand to exceed the speed of light, and the mathematics becomes almost reasonable. Insist on it, and everything strange comes back. The other route people reach for is a wormhole, and it has a longer pedigree. Einstein and Nathan Rosen described a bridge between two regions of spacetime as far back as 1935, though the version they found pinches shut instantly and cannot be traversed. The modern treatment dates to 1988, when Kip Thorne and Michael Morris worked out what a stable, traversable wormhole would require, and they did it charmingly because Carl Sagan had asked Thorne for a scientifically defensible way to move a character across the galaxy in the novel he was writing. The answer they produced is a genuine piece of physics, and it ends in the same place. To hold the throat open, you need matter with negative energy density, in quantity, indefinitely. Nobody has found any. Nobody knows whether any exists, and there is a deeper objection that applies to every superluminal scheme regardless of its mechanism. In relativity, whether two distant events happen at the same time depends on how fast you are moving. Observers in different states of motion genuinely disagree about the order of events that are far enough apart, and normally that disagreement is harmless, because no signal can travel between such events anyway, and nothing that happens in one can affect the other. Introduce any means of sending something faster than light, and the harmlessness disappears immediately. Combine two superluminal trips at different velocities, and you can construct a path that returns to its own starting point before it left. Faster-than-light travel is not a separate capability from time travel. In a relativistic universe, they are the same capability wearing different clothes, and that is precisely why Hawking proposed that the universe must have some mechanism for forbidding it. It is also worth answering a claim that circulates constantly, which is that faster-than-light propulsion has already been achieved somewhere and is being kept quiet. Set aside the question of secrecy entirely, because for once it does not matter. The argument in the rest of this part applies exactly as written to a drive that already exists. A functioning superluminal ship, built and flying tonight, would not be able to reach the edge of the universe either, for reasons that have nothing to do with its engine, and that no amount of classified engineering can address. But we are not doing engineering tonight. We are doing the question in the title, so let us be generous. extravagantly, unreasonably generous. Suppose it all works. Suppose the negative energy problem is solved next Tuesday, the quantum inequalities turn out to have a loophole, the steering problem is engineered around. Hawking was wrong, and by the end of the decade you can travel anywhere at any speed you like, 1,000 times the speed of light, 1,000,000, instantaneous if you prefer. What does that buy you? It buys you a great deal, and I want to be fair about that, because it would genuinely solve one of the two problems in this video. The cosmological event horizon is a limit on how far light can get. If you're not bound by light, you're not bound by it. All those galaxies past redshift 1.6, the deep field, the quasars, the entire early universe would come back into play. The 95% would reopen. That would be the single largest expansion of the possible in the history of the species, and it would be earned. It does not, however, get you to the edge of the universe. Not, it would take a long time. Not, the energy is prohibitive. It does not get you there at all, and making the drive faster does not help, and making it infinitely fast does not help either. Here is the test, and you can run it in your head right now. Go. Instantly. Pick the furthest thing in the sky, the galaxy at redshift 14, 34 billion light-years out, the current record holder, as close to the edge as anything anyone has ever confirmed. Snap your fingers, and you are there. Now look around. The sky is full, in every direction. There is no thinning, no boundary, no wall on one side and galaxies on the other. You're standing in an ordinary patch of an ordinary universe, and out at the margin of your sky there are faint red smudges that were not in your catalogue before you left, because they were outside your old horizon, and they are inside your new one. And the edge of the observable universe is 46.5 billion light-years away, exactly as far as it was when you set off, not 1 light-year closer, and when you turn around and look back the way you came, you do not see home. You have outrun your own past. The light that is arriving at your new position from the direction of the Milky Way left 34 billion years worth of travel ago in comoving terms, which is to say, it left before there was a Milky Way, and it shows you a patch of early universe with nothing recognizable in it at all. Your own galaxy is not visible from where you're standing, not because it is too faint, but because the news of it has not arrived and will not for longer than the sun has left to burn. You are further from home, in every sense that light can measure, than anyone has ever been from anything. Do it again. Pick the furthest thing in this new sky and go there instantly. Look around. The sky is full. New galaxies at the margin. The edge is 46.5 billion light-years away. Do it 1,000 times. 1 billion. Cross a distance so large that the numbers stop being sayable. Every single time you stop and look, you're at the center of a sphere of exactly the same radius, and the edge is exactly where it was. You're not falling behind. You're not going too slowly. You're not being outrun by an expansion. You could be moving infinitely fast and the result would be identical, because the thing you are chasing is not out in front of you at all. That is the whole of it, and we are almost at the point where I can say plainly what it means. But before we get there, I want to look at what happens to this universe if nobody makes the trip. Because the far future of the sky above us has a shape, and it is the strangest argument in this entire subject for why the era you are living in is a piece of luck rather than a default. In 2007, two physicists named Lawrence Krauss and Robert Scherer published a paper with a title that reads like a joke and is not one. They called it The Return of a Static Universe and the End of Cosmology. What they had done was run the current picture forward. Not to the heat death, not to the last star, just forward 100 billion years or so. A length of time that is long compared to the current age of the universe, but short compared to how long the universe has left. And then they asked a simple question. What would an astronomer alive at that point be able to see, and what would they conclude? The answer is one of the most quietly disturbing results in physics. Start with what disappears. Every galaxy outside the local group crosses the event horizon and redshifts away. Not instantly, not dramatically, but completely. Their light stretches further and further into the radio and then past it, dimming as the fourth power of the stretching all the while, until there is no instrument that could ever be built that would register them. The sky empties. Everything beyond the merged remnant of the Milky Way and Andromeda goes dark, and the darkness is not a failure of the telescope. There is simply nothing arriving. So that astronomer looks up and sees one galaxy. Theirs, surrounded by nothing, in every direction, out to the limit of any instrument. It is worth being clear that this is not a dead sky. That single remaining galaxy is still working. It has gas, it has dust, it is still forming stars out of the material its dead ones left behind. And the smallest of those stars, the red dwarfs, burn so slowly and so frugally that they will still be shining 10 trillion years from now, which is a length of time next to which the entire history of the universe so far is a rounding error. There is nothing bleak about the astronomers' local situation. Their galaxy is warm, populated, and going nowhere. It is only the sky outside it that has closed. Now take away the second pillar, the cosmic microwave background, the single strongest piece of evidence that the universe had a hot, dense beginning. The thing that settled the argument in the 1960s has been stretching this entire time along with everything else. In 100 billion years, its wavelength will have been stretched past the size of the horizon itself, not too faint to detect. Longer than the observable universe is wide, which means it cannot be detected even in principle by anything, ever. And the third pillar goes too. One of the strongest confirmations of the standard picture is the primordial abundance of the light elements. The precise ratio of hydrogen to helium to lithium produced in the first few minutes, which matches the prediction to remarkable accuracy. But stars have been processing that material continuously, fusing hydrogen into helium and helium into everything else, and blowing the results back out. After 100 billion years of that, the composition of the gas has been so thoroughly overwritten that the primordial signature is gone. Measure the helium fraction, and you get a number that reflects 100 billion years of stellar recycling, not the first 3 minutes. So here is the astronomer. They have an excellent telescope. They are careful, they are rigorous, they are honest, and their instruments are better than ours. They point that telescope at the sky, and they measure. They find one island of stars, held together by its own gravity, showing no expansion because bound structures do not expand. They find nothing beyond it. They find no background radiation. They find no elemental fingerprint of a beginning, and they conclude, on the basis of every piece of evidence available to them, that the universe consists of a single galaxy in an eternal static void, that it has always been this way, and that it always will be. They will be doing perfect science. Their reasoning will be flawless, their data will be excellent, their conclusion will be completely wrong, and there will be nothing anywhere in their sky to tell them so. I find that harder to sit with than any of the distances in this video, and I think it is because of what it implies about us. It means that the ability to know what kind of universe you live in is not a permanent feature of being an intelligent observer. It is a temporary condition. It depends on being alive during the window when the evidence is still in the sky, and that window is not a small fraction of the universe's history in some abstract sense. It is over. And Krauss and Scherer made one further observation in that paper which is, if anything, worse than the main result. If it is possible for a competent observer to be structurally deceived by an emptying sky, then the obvious question is whether it has already happened to us. Not in the same way, the galaxies are still here, the background radiation still arrives, but in some other way, about something we have not thought to look for. Is there information about the early universe that was available to an observer 10 billion years ago and is no longer available to anyone? Is there some feature of the cosmos that has already redshifted, decayed, or been overwritten past the point of recovery, so that the standard model we have built is not wrong so much as it is missing a page nobody knows exists? There is no way to answer that. It is not a question with an experimental design. But it changes the character of every confident statement in cosmology, including the ones in this video from "this is how it is" to "this is how it looks from here, now, with what has survived." We happen to be here early enough that the galaxies are still visible, that the background radiation still arrives, that the fingerprint of the first 3 minutes is still readable in the gas. Every one of those is a wasting asset. We did not earn the view. We arrived while the lights were still on, which is why the last piece of this matters more than its status in the literature suggests. There is an instrument on a 4-meter telescope at Kitt Peak in Arizona called the Dark Energy Spectroscopic Instrument, which takes 5,000 spectra simultaneously through 5,000 robotically positioned optical fibers, repositioned between exposures. It has been building the largest 3-dimensional map of the universe ever made. Its second data release rests on about 14 million galaxy and quasar redshifts, up from 6 million in the first. The technique it uses is worth a moment, because it is one of the more elegant measurements anyone has devised. In the first 400,000 years, before the universe went transparent, pressure waves travelled through the hot plasma, actual sound waves at enormous wavelengths, rippling outward from every overdense patch. When the universe cooled and the plasma became neutral gas, those waves stopped travelling and froze in place, leaving a faint preferred separation between clumps of matter of about 490 million light-years. That frozen ripple is still imprinted on the distribution of galaxies today, and it acts as a ruler of known length lying across the sky. Measure how large it appears at different distances, and you can read off how fast the universe was expanding at each epoch. It is a fossil of the sound of the early universe, used as a measuring stick, and it has been finding something that nobody was looking for. When the DESI measurements are combined with cosmic microwave background data and with supernova samples, the FIT prefers a dark energy that is not constant, something that was stronger in the past and has been weakening. The reported significance sits somewhere between about 2.8 and 4.2 standard deviations, depending on which supernova compilation goes into the analysis, which is well short of the threshold physicists require before calling something a discovery, but which has now survived 2 data releases and has strengthened rather than faded as the data volume doubled. Fresh results from the Lyman Alpha Forest, released at the end of last month, continue to bear on the question. If it holds, the implications reach directly into everything we have been discussing. A dark energy that weakens is a dark energy that eventually stops accelerating the expansion, and an expansion that stops accelerating does not have a converging event horizon. The wall at 16.7 billion light-years would begin to move outward. Galaxies that we have written off, some of the 95%, would come back into the reachable column. The ending would be different. The emptying sky might not empty, and the astronomer in 100 billion years might still have something to look at. I want to be careful with that, because hope is easy to oversell, and this is a 3 sigma hint, not a result. It may evaporate. Several of the most exciting hints in the history of cosmology have. The Vera Rubin Observatory's 10-year survey and the Euclid mission are both now returning data of the kind that will settle it one way or the other within the decade. But it does mean something important about everything I have told you tonight, and I would rather say it plainly than let it sit as an asterisk. The boundary at redshift 1.6 is drawn using our best current model of what dark energy is. It is not the law of nature. It is a measurement taken during a particular decade by people who are still arguing about it. The edge, though, the 46.5 billion light-years, the thing in the title, that one does not depend on any of it. That one is settled, and it has been settled since the first careful person thought about what a horizon is, and it is time to say plainly what it is and why we will never make it. So here is the answer, plainly, with nothing held back. What it actually takes to reach the edge of the universe is not a ship, or a fuel, or a speed, or a length of time. Those were all the wrong category. The reason we will never make it is that the edge of the universe is not a distance at all, it is an age. 46.5 billion light-years is not the size of anything. It is the width of 13.8 billion years, converted into a length by the speed of light, and then inflated by everything the expansion did to that light while it was in transit. When you look out at the boundary of the observable universe, you're not looking at the far side of a container. You're looking at the exact surface where the amount of time light has been travelling equals the amount of time there has been. That is the whole of it. The edge is the place where you run out of past, and a place where you run out of past is not a place you can travel to, because travelling does not give you more past. It gives you more distance, and distance was never what was in short supply. Let me finish taking you there one last time. You're moved instantly, never mind how, 1 billion light-years from here. You stop, and you look outward in the direction you are heading, and the edge of the observable universe is 46.5 billion light-years away. You are moved 10 billion light-years. You stop. The sky is full. There is no thinning, no boundary, no last row of galaxies. At the margin, there are faint red smudges you have never seen before, because they were outside your horizon this morning and they are inside it now. The edge is 46.5 billion light-years away. You're moved to the furthest thing anyone has ever confirmed, 34 billion light-years out, and then past it, and then past whatever is at the margin from there, and then again and again, for as long as you like. 1,000 jumps, 1 billion. Distances with no names, and every single time you stop and look, the sky is full, and there are new galaxies at the edge of it, and the edge is 46.5 billion light-years away. Not closer, not once, not by a single light-year, at any speed, including infinite speed, in any direction, ever. Because you have not been chasing something out in front of you. You have been carrying it. You're always at the centre, that was the phrase, back near the beginning, when it sounded like a harmless piece of trivia about there being no middle to the universe. It is not trivia. It is the entire mechanism. You are always at the centre of your own observable sphere, which means the boundary of that sphere is always exactly the same distance from you, which means arriving at it is not difficult, or expensive, or slow. It is not a thing that can happen, and the light is still arriving. That phrase has done 3 different jobs tonight, and this is the last of them. In part 3 it was reassurance. Even from galaxies receding faster than light, the photons get through. In part 6 it was grief. The light is still arriving from places we can never reach, and its arrival is not contact but the last of it. Here at the end it is simply the definition. The edge of the observable universe is nothing more or less than the place where light has only just this moment finished arriving. It is not made of matter, it is made of timing, and it moves outward at exactly 1 light-year per year, forever, for everyone, whether they travel or stay home. It is worth saying what the word reach was quietly doing all evening, because it turns out to have been the problem. To reach something is to close a gap between where you are and where it is. That requires it to be somewhere, to have a position that stays put while you approach. Every destination anyone has ever had, from the far side of a room to the far side of the solar system, has had that property, which is why we never noticed it was a requirement. The edge does not have a position. It has a relationship to a position, and the position it has a relationship to is yours. Ask where it is, and the honest answer is not a coordinate. It is 46.5 billion light-years from whoever is asking. Move the asker, and you move the answer. There is nothing to close a gap with, because the gap is not between 2 things. It is the size of 1 thing, and the thing is you. That is also, incidentally, why the question can only ever be answered and never solved. A question with a clean, correct, complete answer that still leaves nothing to do is a rare object, and this is one of them. And there is a reciprocity in it that I keep coming back to. Somewhere out at the margin of your sky tonight, 34 billion light-years away, there is a region we can see as it was 280 million years after the beginning. If anything is standing there now, and the universe has had 13.5 billion years to arrange that, then they are looking outward at a sky exactly as full as yours, with a boundary exactly as far away, and somewhere near their margin is a red smudge that will one day be the galaxy you're sitting in. Neither of you is at the edge. Both of you are at somebody's edge, and the 2 of you will never exchange a single photon in either direction, because you are on opposite sides of the 16.7 billion light-year wall, and you always were. So there are 2 answers to tonight's question, and they are different in kind, and both of them are true. The first answer is the hard one, and it is about a wall that genuinely exists. The cosmological event horizon, 16.7 billion light-years out, redshift 1.6 drawn by the accelerating expansion. Around 95% of the galaxies you can see are on the far side of it. Nothing we send from tonight will ever reach them, and nothing they send from tonight will ever reach us. And the light that keeps arriving from them for the next billions of years is the tail of a correspondence that has already closed. That wall is real. It has physical consequences. It may be moving, and the instruments that will tell us are taking data right now. The second answer is the one in the title, and it is not about a wall at all. We will never reach the edge of the universe because there is nothing there to reach. Not too far, not too fast, not there. It is the shape of what it means to look at things from somewhere, and everyone who has ever looked at anything has had one, and they are all exactly the same size. I want to end on that rather than on the 95% because I do not think it is a defeat, and I have thought about this a great deal. It is easy, and often accurate, to describe the universe as hostile or indifferent, or a set of doors quietly closing. Some of that is fair. The horizon is a real loss, and it deserved the part of the evening we gave it. But the edge is a different thing entirely. The edge is not the universe refusing us. It is the universe telling us, in the only language it has, that a point of view is a real physical object with a real physical size, that having a place to stand costs something, and what it costs is everything that has not had time to reach you yet. That is not a wall. That is a description of what it is to be somewhere, made by something that has been patiently expanding for 13.8 billion years and does not appear to be in any hurry. And there is a strange comfort in it, once you stop trying to get there. In a universe where almost everything is receding, where the reachable sky is shrinking every second, where a galaxy crosses out of reach tonight and nothing anywhere registers the moment, there is exactly one thing that will never get further away from you: the edge. It has been 46.5 billion light years away for your entire life. It was that far when you were born. It will be that far on the last day of the universe for whoever is left to look. Every other thing out there is leaving. That one stays exactly where it is, no matter what you do, no matter where you go, no matter how fast. You will never make it. Nobody ever will. And it will be waiting there, unchanged, the same distance from anyone in the universe who happens to look up, for as long as there is anyone left to look up at all. There is one thread I'm going to leave hanging gently, because it is the one that stays with me longest after the lights go off. Beyond the edge, beyond the region that has had time to send us word, there is a further boundary at about 62 billion light years, the absolute limit of what will ever become visible from here, however long the universe or its observers last. Everything inside it is on its way. Everything outside it is not, and never was, and never will be. And there is almost certainly something out there. The geometry of space, measured to about 2 parts in 1,000, comes out flat, and a flat universe in the simplest reading does not stop. It may be infinite. It may contain regions where the physics settle differently, or where nothing ever formed, or where the same slow accumulation of dust into stars into planets happened and is happening still. We will never know, not through better instruments, not through more patience, not through any conceivable advance. The universe has drawn a line around what can ever be evidence, and the line is not a matter of technology, and it is not moving. Which means that for the rest of time, the largest true statement anybody in this universe will ever be able to make about it is a statement about their own small-lit sphere, 46.5 billion light-years across, with themselves in the middle of it, surrounded on all sides by something they can be quite certain is there and can never say one word about. That is where we are. That is where everyone is. And the light is still arriving.